Okay, so now I want to discuss some of the terminology and definitions, mathematical definitions associated with probabilities. Okay, we talked a little bit at a high level previously, and you can notice that we introduce some terms such as the idea of something having an expectation, perhaps, the idea of a probability, the idea of an outcome, the idea of having an experiment. Okay, so the first thing I'll do is I discuss some terminology associated with these. Okay, and then next we'll talk a little bit about a kind of mathematical definition for probability, or at least in discrete spaces. Okay, so terminology. Okay, so in probability it's useful to think of something as considering experiments. Okay, so these are essentially something that has a set of outcomes, it has a set of things that can happen, a sample space, and we then look at the outcome that occurs from this experiment. Okay, so sometimes we consider in probability experiments. Okay, we can have quite a broad definition of what we really mean by an experiment in terms of what goes on in the real world. Okay, but it could be something like we throw two dice, okay, and we add up the sum of those two numbers. Okay, so e.g. throw two dice and add the total. Okay, so that will be perhaps an experiment. Okay, and an outcome is what we observe from that experiment. Okay, so that is the result of the experiment. Okay, so for example, okay, we might get from the first dice, we might get a 5, okay, and from the second dice, we might get a 2, and then we add them together, and the result of the experiment is 5 plus 2, which is 7. Okay, so in that case, in the experiment, which is throw two dice and add the total together, the outcome is 7. All right? Okay. Then, with the experiment, we also have associated with it a sample space. Okay. So that is the sets of outcomes that can occur. Okay. Okay, so the sample space, okay, which in this case we might denote by S, or we might denote by omega, okay, is the set of possible outcomes. Okay, so e.g. in our dice throwing experiment, omega, which will let be a set. Okay, so remember a set is something with these sort of curly brackets. Okay, it's a set of numbers. So you can either get 2, 3, 4, all the way up to 12. The sets of things that could happen as outcomes from our experiment. One thing to notice at this point is that when we define, there is some ambiguity in the way we define a sample space. For example, I could have done the numbers between 1 and 12, although there's zero probability of the event of 1 happening, I could still include it in my sample space. Okay, Also, I could look at the experiment, okay, of 2 dice being thrown, and I could keep a sample space, okay, which consists of the outcome of the first dice and the outcome of the second dice, okay. And in that way I could have a further sample space which consists of all the pairs of outcomes of the first dice and the second dice, okay. And then from that I could infer the outcome of the experiment as well, okay, essentially just by summing these 2 numbers up, right. So that's one thing to take account for, that there isn't a unique way to represent an experiment, okay. It doesn't mean there isn't a way you can specify a particular experiment, okay, but there just might not be a unique one, okay. Alright, so next. So then we might want to ask questions about the sorts of things that can happen, okay? And an event is a subset, of outcomes from the sample space. Okay. So, for example, we can ask things like, in this case, the outcome was a 7, so we might consider the event E, which is the set which consists of a 7 occurring, okay? Or we could ask about the event where it's a 7, or it might be a 4, okay? So here we're interested in the event where we get a 7. It belongs to this set. The outcome belongs to this set, so it could be either a 7 or it could be a 4, okay? Or we could ask slightly more abstract things, okay? So we don't need to specify the set as a list necessarily in this way. So it's quite common in probability to do things where we say, consider the event, okay, where we get an even number. And I should be a little bit more specific, between, so an even number between 2 and 12. Although implicitly I'm assuming that the event is a subset of omega. Okay, so we could ask just that E is an even number. Okay, but notice here I haven't explicitly written out all the numbers that have to occur. I've just written down it has to be an even number, and through knowing what an even number means as a subset of this set, I can infer what that means. Okay, exactly which elements of this set that refers to. So exactly which outcomes I'm interested in. Okay? Right. So there are plenty more examples that one could do. I maybe won't list them here completely, but let's just write them. Oh, maybe I will. Okay, so just some examples. Okay, so we could look at some sort of examples of experiments and sample spaces. So we could consider a type of experiment and sorts of sample space associated with that. Okay. Okay, so we could consider throwing 2 coins. Okay, and here I could have a outcome which consists of what happens with the first coin. Let's say it's a head. Okay, and what happens with the second coin. Maybe that's also a head, and that would be one outcome in my sample space. And then I could go about listing all the sorts of outcomes that occur. So it'd be heads, heads. Then we get heads for the first and tails for the second. Okay, then maybe tails for the first and heads for the second, and then tails for the first and tails for the second. Okay, and that would be a reasonable sample space for that experiment. Okay. I could also look, like I mentioned above, is that I just look at the experiment that consists of throwing 2 dice. Okay. Okay. And here, all right, this would consist of the outcome of getting, say, a 1 and a 1. Okay. Or I could look what happens with a 1 and the second dice being a 2. All right. And then go all the way up to 1 and a 6. Okay, so the first dice gives me a 1, second dice gives me a 1, first dice gives me a 1, the second dice gives me a 2. Okay, and then I could look at the case where the first dice is a 2 and the second dice is 1 and continue 2 and 2 all the way up to 2 and 6. Okay, and I could keep going down. It'll take me a long while to write all this out completely, so I'll just skip a few steps to where the last dice is a 6 and the second dice is a 2. Okay, all the way to a 6 and a 6. Okay, now I've written this out purposely as a sort of grid. Okay, and that's something that's sort of important, because notice, as we sort of suggested earlier with the case of a dice, okay, the chance of getting a 5 was 1 in 6, and that's because there's 6 equally likely outcomes. Okay, in the same way it happens if we throw 2 dice, okay, and the outcome of the first dice does not affect the outcome of the second dice, okay, then all these outcomes are equally likely. Okay, so if I was to ask if any one event was to occur, such as getting a 1 followed by 1, okay, the chance of that happening will be given by the number of outcomes in this sample space. Okay, now if we look at this sample space, because it's a grid like this and it's a 6 times 6 grid, then we can guess at what the probability of a 1 and a 1 is. Okay, well, it's the number of items in here, which is 6 times 6, so 36. Okay, so we can then get the idea that the probability of a 1 and a 1 is 1 in 36. Okay, so that's an important point, that we're going to be getting into the idea of having to do lots of counting with different sorts of sample spaces in order to understand certain things in probability, particularly for discrete probabilities. Okay, all right, so next time I'll start to discuss in a little bit more detail different types of counting rules. Okay, this is something that could well be done in a pure mathematics course and equally done in a probability course. It comes up a lot in discrete probability. Okay, so we'll try to cover some of that. Okay, right, let's keep going with some other examples. Okay, we could look at other things, which would be like, say, the number of clicks from a Geiger counter. Okay, so if we have a nuclear reactive material, okay, and it is one that, say, lets out certain, say, gamma rays, okay, each particle in there over a given time has a chance of decaying and letting out, say, a gamma particle, and then we look over a period of, let's say, a minute or so and count the number of decays that have occurred, or the number of gamma rays that have been counted. Okay, there, if we observe over any given minute, we're going to get a number which is, either we observe nothing, or we might observe 1 gamma ray, or 2, or any number. Okay, so we can consider sample spaces which are discrete, okay, but also infinite, right? So there's no definite end to this list. Okay, it's a discrete type of infinity. We can count all the elements in this list. Okay. Another example that might be different is we might want to consider, say, people's heights. So we might choose a person at random and ask what their height is. Okay, and there we might want to specify a sample space that is continuous. We know people's heights are, say, positive numbers. Okay, but continuous now. All right. Now, for the at least for the better part half of this course, we're going to focus on the discrete world. Okay. But we will then begin to move on to situations like this, where we look at, say, heights, where we've got something that's a continuous random variable, a subset of the real numbers, or a subset of the real number to some higher dimension. Okay? Okay, so that's to keep in mind for what's going to go ahead. Okay, but for now, we'll mostly focus on discrete probabilities. Okay? So let's go to that. So let's go through a sort of definition of probability I'll probably say probability, being a little bit careful here, probability space. Okay, and we're going to only focus, so one thing to say, just to get rid of that, we're going to only focus on the discrete case for now. Okay. So for a sample space, omega, okay, which will keep it discrete, so it consists of an omega 1, an omega 2, an omega 3, and it could be finite or it could keep on going forever. All right. So for this, in the mathematical sense, when we're mathematically considering things, probabilities are numbers. Okay, so something like P of omega 1, and I'll put a little extra curly brackets there because I'm considering a set, okay? I'll delete the 1 here. P of omega for each omega in the sample space. So for each outcome that can occur in my sample space, I associate a number, okay? And then there are relations between these different numbers, okay? So the two key properties that we need are, so probabilities are numbers such that for each omega, such that these numbers, okay, P, I'm going to kind of ignore this curly bracket now. Formally I should have it there, but I'm not going to because I'm lazy. Numbers that are positive, okay, for each omega belonging to my probability space, okay. Also, for those of you who haven't seen this sort of mathematical definition, this means this belongs to, so this for each outcome which belongs to this set or list of outcomes, okay. Also, I tend to personally write probabilities like this. I tend to have a kind of double bar notation, so I kind of go like a probability looks like this, and later we'll see things like an expectation which will look like this, and also things like indicator functions which I'll draw like this, okay. So I tend to use for things that are asking questions, okay, about likelihoods in a sample space. I tend to use this double bar notation, but that depends on the author, okay. Anyway, so probabilities are numbers that are positive, okay, and also we're going to assume that the sum of these positive numbers sums to 1. So if I sum over all the outcomes that can occur in my sample space, then the sum of these outcomes must be equal to 1. Okay. Notice this makes a constraint, okay, that says that probabilities are numbers that are positive, and also they must be less than 1. Each individual one of these numbers to satisfy these two constraints must be between 0 and 1, like I discussed earlier. Okay. One thing to say is that, for example, when we were considering the dice throwing example, where you say that the chance of 5 occurring is 1 in 6, okay, notice if I summed up each of those likelihoods, okay, so the chance of a dice being a 1, a 2, a 3, a 4, a 5, or a 6, okay, well, one of those things has to occur, right? And so then if I look at the sum of the probabilities, okay, which I think of as being the chance that one of those things occurs, well then the proportion of time that one of those things happens is 1. All the time I expect either a 1, a 2, a 3, a 4, a 5, or a 6. Okay? So that kind of leads us on to how we think about events occurring. So more than just one outcome occurring, but sets of outcomes occurring. Okay? Okay, so events let's say A, okay, which is a subset, okay, so this means a set of outcomes which belong to this larger set, okay, we get probabilities by summing. So again, just like here, I've introduced a new mathematical notation for those who are not aware of it. This means belongs to. This one means subset of. So this means some list of outcomes which are contained in this larger list. Okay? All right. So we get the probabilities for events by summing. Okay? So if I wanted to know the probability of event A occurring, all I need to do is sum up the probabilities of all the outcomes that can occur in that set. Okay, and for each one I'm going to sum up the probability of that, and that gives me the probability of the event A. All right. Now that's a pretty good working definition of probabilities. Okay. For a discrete sample space. Okay. Notice that really what I can think of as this probability is really sort of a function, okay, from the sets of subsets of this sample space. Okay, so let's say this number, this special thing 2 to the omega, represents all the subsets that I can ask of this sample space, and then I take a function of those. So for each element in there I get a number, okay, a number between 0 and 1. Okay, so that's essentially what a probability does. Okay, now just as a bit of a look ahead, in practice, when we deal with, well, not in practice, but when we start to extend the notion of discrete probabilities to, say, different sorts of spaces, which are, say, continuous or neither continuous or discrete, but if we want to generalize our notion of probability, we have to be a little bit careful about what sets of things we're allowed to associate probabilities with. Okay, so sometimes it's useful to consider some set, which I'll denote by this kind of fancy script f, okay, which is a subset of the sets of subsets of the sample space. Okay, and then we consider a probability to be a function from this special set of subsets I'm allowed to deal with to 0, and 1. Okay. Now, this is a little bit of an aside, and this is the kind of thing that when you come into a second year probability course, you'll see in a little bit more detail. Okay, but essentially, through this, we can think of probabilities as consisting of three things: a set of outcomes, okay, a set of events that we're allowed to deal with, which I'll denote by F, and a special function, this probability function, or sometimes called probability measure, which takes the sets of events that we're allowed to consider and then assigns them a probability. Okay, so let me just write that down. A probability space consists of a sample space okay, so what do I mean here? Just the sets of things that can happen, omega, a set of events that can be considered, F, and like I say, for now, assume that's just everything you can think of. Later on in your mathematical careers, you'll see that you have to restrict that a little bit. Okay, and a probability measure okay, P, which, like I say, is a function from these events 2, 0, 1, which obeys the rules above. So what do I mean by the rules above here? I mean that the sum of all the probabilities over the sample space is 1, and that they're all positive. Okay, so those are the rules that the probability measure has to satisfy. Okay, so when we sum up the probabilities of all the individual outcomes, it must sum to 1. Okay, but let's not worry too much about that. Essentially, let's just think of probabilities being numbers that if we sum up all the outcomes, they go to 1 and they're positive. Okay, right. Okay, so that's a little bit abstract. Let's be a little bit more concrete now. So an example. So let's look at the probability. Let's consider the experiment, okay, where we throw 2 coins, okay. And we're going to look for the probability that we get at least 1 head. Okay, so let's answer that question. You can probably answer that on your own fairly well, but we'll do that within the kind of framework which we've just discussed. Okay, so let's answer that. Now, this is not necessarily for kind of an exam type of question, it's just us discussing our way through the definitions that we've given above with this specific example. Okay, so in this case, our sample space is going to be, as we described before, heads, heads, we'll get heads, tails, we'll get tails, heads, we'll get tails, tails. Okay. Now, One thing, like I discussed previously, is that, well, all of these 4 outcomes are equally likely, okay, because we're assuming that the coins that we're dealing with, or at least implicitly in this question, is they're both unbiased, as in they both give 50-50 chance of heads or tails, and we're assuming that they're independent, meaning that the outcome with the first coin doesn't affect what happens with the second coin, okay? So then, in that case, all these outcomes should be equally likely, okay? So each of these So each outcome is equally likely. Excuse my bad spelling. So there is a probability P such that the probability of heads is equal to the probability of heads tails is equal to the probability of tails heads and is equal to the probability of tails tails, okay? And so as we know that the sum of all of these must be equal to 1, we know that the sum over all the events, these 4 events, of each of these guys, okay, must be equal to 1. This means that if we look at this sum, we're just summing up P 4 times, so we know that 4P equals 1, which implies that P equals 1 over 4. Okay? So then we have the probability, under the assumption that all these events are equally likely, we have the probability of each event occurring. Okay? So now we need to use our rule from above, okay, to get this rule from above, that the probability of the event we want to consider is the sum of the probabilities of each outcome. Okay? So, really, the event of at least one head, at least one head, okay, I could write that down a little bit more explicitly. That's the event where, well, if I get heads heads, there's definitely one head in there. If I get heads tails, there's one head in there. And if I get tails heads, okay, there's also a head. And we exclude the tails tails case because that's not included in the situation where there's one head, or at least one head. Okay? So, from this we can apply a rule above, that the probability of this event, okay, is equal to the sum of the events in this set. Okay, so I'm writing this a little bit slowly, but all I'm doing here is I'm taking this definition and just applying it. Okay, now I know I'm summing up each of these events is equally likely, got a probability P, and there's 3 of them. Okay, so I'm going to get 3 divided by 4. Okay, so essentially this is a very long-winded way of saying, well, the probability of this event is just the number of elements in this set, 3, divided by the total number of elements in the sample space. Okay? So that's one way we can use those rules above to calculate the probability of at least one head. Okay? But there are other ways we could do this. Let's just do one more, which uses a little bit of a trick. Okay? Well, we can notice that the probability, okay, of at least one head has 3 elements: probability of head head, probability of head tails, and probability of tails head. Okay, and there's one thing that we've left out: probability of tails tails. Okay, so I know if I added this to the probability of tails tails, I would have included all the sorts of outcomes that can occur. Okay? So we know that the sum, if I sum out all the outcomes, I get 1. So I know that this, which includes the first 3 outcomes, plus this, which includes the final outcome, well, the sum of these probabilities must be equal to 1. And I know the probability of tails tails, that's equal to a quarter. Okay, so I know this is equal to a quarter. So then I can then solve that the probability of at least one head is 1 minus 1/4, which is equal to 3/4. Okay, so that's 2 different ways of looking at doing this calculation. The first way here, all right, we looked at counting. We counted the number. We essentially counted the number of outcomes where there's at least one head, and there were 3 of those. So that gave this 3 here. And then I also counted the number of outcomes. That gave this 4 here. Okay, and we've got 3/4. This was a slightly different way of doing it. We looked at the sets. We looked at this. There's a set of at least one heads, and there's a set where there isn't at least one head, which means tails tails. Okay, I didn't need to do any counting to work out that well, not very much counting to work out that the probability of tails tails is 1/4. Okay, and then I could rearrange, okay, to get the answer. So one was a rule that used counting, the other was one that looked at the sets and the relationships between the different events that we were considering. Okay, so what we're going to do next, okay, is first look into this sort of counting viewpoint, and then we'll look into the kind of sets and the way we look at the relationships between different sets. There's lots of rules for doing these sorts of calculations. Okay.